All right, today we're pulling back the curtain on one of the most important ideas in all of computer science, the hash table. This is the secret engine, the powerhouse that makes everything you do feel instant. Let's dig in.
I mean, seriously, think about it for a second. You've got maybe thousands of contacts in your phone. You type one or two letters, and bam, the right person just appears. There's no loading bar, no waiting. How does it do that? Well, it's not magic, it's just some really, really clever engineering.
So, to understand this, we have to start with a basic concept called a dictionary. All it is a way to store information in pairs. You have a unique key, like the name Paul, that points to a value, like his age, 29. That's it. This simple key-value idea is the bedrock of this whole system.
Okay, so let's get into the magic of these dictionaries. What makes them so incredibly powerful? It really all boils down to one thing: raw, unbelievable speed. A dictionary really only has three main jobs. You need to be able to search for something using its key, you need to be able to insert a new key-value pair, and, of course, you need to be able to delete one. And the trick is, all three of these have to happen in the blink of an eye. Now, the ultimate goal here, the holy grail, is what we call constant time, or if you want to sound like a programmer, O of 1. And what that means is that the time it takes to find one contact should be the exact same whether you have 10 contacts or 10 million. The size of your list just doesn't matter. Wild, right? That's the goal. So how on earth do we actually build something that can achieve that kind of performance? Well, this is where we get to the blueprint. We're going to build ourselves a nifty little machine called a hash table. The process is actually beautiful in its simplicity. It's just 3 steps. First, you take your key, let's say the name Paul. Second, you feed that key into a special mathematical recipe called a hash function. And third, that function just spits out a number. And that number, that's the exact address, the index, where we're going to store Paul's info inside a simple list.
And here it is in action. It's so cool. Our hash function took the name Paul and it gave us the number 7. So we stick his data right there in slot number 7. It took Jane and gave us 1. Alex got 0. See how it works? Later on, if we want to find Paul, we don't have to search the whole list. We just run Paul through the function again, it gives us 7, and we jump directly to the right spot. It's instantaneous.
But you knew there had to be a catch, right? With any clever machine, there's always a potential glitch, and this is a big one that our perfect system is absolutely guaranteed to run into.
Okay, so let's say we want to add a new guy, Josh. We run his name through our hash function, and it spits out the number 1. Uh-oh, wait a minute. Jane is already living at index 1. So, what do we do now? And you can see the problem right here on our table. Josh is trying to move into spot number 1, but it's already occupied. This is the exact moment that every single hash table has to be designed to handle.
Yep, this has a name. It's called a collision. It's when our hash function accidentally assigns 2 different keys to the exact same spot. And here's the thing. It's gonna happen. It's inevitable. So how we deal with it is what really makes a hash table truly great.
So our machine has a glitch. Time for a fix. And it turns out there are 2 main ways to think about this. 2 different engineering philosophies for handling these collisions. And these 2 strategies are kind of fascinating. On one side, you have chaining. It basically says, hey, index 1 is full? No worries. We'll just start a little side list at index 1 and put both Jane and Josh on it. But then you have open addressing, which says, nope, index 1 is full. Let's just go look for the next empty spot somewhere else inside our main list. 2 totally different approaches to the same problem. Now, before we go any deeper, we need to talk about one really critical number, the load factor. You can just think of it as our how full are we meter. It's just the number of items we have divided by the number of total slots available. If this number gets too high, our table gets too crowded, collisions happen way more often, and everything slows down. So the number 1 rule is keep the load factor low. So let's focus on that open addressing idea for a second, the one where we look for an empty spot. Turns out we can actually upgrade this method to be a lot smarter. The most basic way to do this is called linear probing. It's dead simple. If spot 1 is taken, you check spot 2. If 2 is taken, check 3. You just probe linearly, one by one, until you find an empty space. It's easy to understand, but it has a sneaky hidden problem. And here's that problem. You can see it right here. When you use linear probing, you end up creating these long traffic jams, these big clumps of filled slots.
Look at this cluster from index 0 all the way to 4. This is really bad news for our performance.
Yeah, this clustering is the big weakness of linear probing. Because if a new item happens to land anywhere in this block, it has to travel all the way to the end to find a spot. An operation that should be instant starts to take longer and longer. We need a way to break these clusters up.
And the solution is a really elegant upgrade called double hashing. This is pure genius. When a collision happens, instead of just checking the next spot over, we use a second, totally different hash function to calculate a unique jump size. So instead of checking spot I+1, maybe we jump ahead 5 spots or 8 spots. This scatters the colliding items all over the table, which stops those performance-killing clusters from ever forming in the first place. So clever.
Okay, so we've built our machine, we've fixed the glitch, and we've given it a serious upgrade. Let's look at the final spec sheet and see what makes it so efficient.
Believe it or not, we can actually predict the performance with this simple little formula. Now, you don't need to be a math genius to get this. All it's saying is that as long as alpha, our load factor, stays low, let's say we keep the table less than 2/3 full, this whole thing works out to be a very small constant number. It means on average, we'll only ever have to check maybe 2 or 3 slots to find what we're looking for. That is a constant number. That is our O1 performance.
So let's wrap it up with our toolkit. It's really 3 key things. 1, a super fast hash function to turn our keys into addresses. 2, a smart collision resolution strategy, like double hashing to handle any conflicts. And 3, we keep an eye on our dashboard gauge, the load factor, to make sure our table never gets too crowded. Put those 3 things together and you get that beautiful instant search we all rely on. And that's the hash table. It's not magic, it's just an incredible piece of engineering. So the next time you search for a file, look up a word, or pull up a contact, you'll know the secret sauce that's making it all happen.